So today we are going to go over latches and flip-flops. Your lab this week is going to be on making latches and flip-flops. And we're also going to go over sequential logic. So first, what is a sequential circuit? It's a circuit whose output depends on not just the current inputs, but also the past outputs. So there's some kind of feedback loop into this circuit, which gives it a memory because it remembers what it was outputting before, and it's a function of that as the input. So why do we need circuits with memory? So circuits with memory can be used to store data. Right? You have registers in your CPU, you have your CPU cache, you have your DDR, which is your main memory. And then there's the other circuits like a hard disk drive. And systems have circuits that run like a sequence of tasks, and they need to have this memory to remember what the last step was so that they can go on to the next step. So this is like your simplest memory unit. Let's first, there's no input at all. Let's just say that we connect this load and our data is 0. Okay. Then here, it comes in as 0. It gets flipped to 1, and then it gets flipped as 0 at the outputs. And let's say that we very quickly disconnect that, so we're not driving it anymore, and we connect remember. And now we just have this stored value. But this stored value is coming back up here. So this is 0 over here, and 0 up here. It's going to get flipped, become a 1, and then get flipped again, and it remembers it's 0. So it kind of has this memory. This is a very simple version of this. But you can make these circuits with memory. This one, you would have to keep it powered. Otherwise, as soon as it loses power, it's not going to be at steady state, and it's going to forget what it was. So here's an example of needing a memory. So like you're on an airplane and you have that button to call the flight attendant over. When you click the button, even though you're not holding the button anymore, the light stays on until the flight attendant comes and then clicks a different button to indicate that they helped you with whatever you needed. So there's some sort of memory to store that the button was originally pressed before it was the other button was pressed to turn it on. Because otherwise you'd have to continually hold the button to keep the flight attendant light on. So the logic circuit to implement this, we could use a SR latch, and the S stands for set and reset. So set reset latch. So the way it works is you have access to this button, and they have access to the reset button. It's labeled cancel button here. And it's implemented with these NOR gates. So just as a reminder, I have A, B, 0, 0, 1, 1, 1, out. If I am a NOR gate, this is my output. right? So say no one's pushing these buttons, and we have 0 here, 0 here. Then that means that we don't really know what's coming out the output yet, because it depends on what Q and this were. So let's simplify this first. Let's say I want to call the flight attendant. So I'm going to push the button. And they're presumably not pushing the button. So if I have a 1 here, no matter what this input is, it's going to become a 0 out here. And then that is going to be fed back over here. So I have 0, 0. That means this is going to become a 1. And then that is going to be fed back here. It's 1. It doesn't change my output. So now I have the light is on, and this other output up here is 0. But now let's say I let go of the button. So I let go of the button. This is still 1, and this is 0. But now this is 0, and this is 0. Okay? So let's follow this. So 0, nor 0. This is still going to be 1. And then this is going to come over here and act as my other one. And this is still going to be 0. So when you have no input, 0, 0, it's going to stay whatever it was before. And now let's say the flight attendant comes to your seat, helps you out, and presses the cancel button or reset button. So this is 0. 0 nor 1 is 0. Your light is going to turn off. 0 is going to come over here. 0 nor 0. This is going to become 1. And then this is also going to feed back here. 1 nor 1. So this stays 0. So you push the button, and when you let go, it remembers until you reset it. And same thing when you hit the cancel button, it remembers that it needs to stay off until you hit the set button. So this is like a very simple memory circuit. So to summarize, and here's our two input outputs. We'll call them, and they're supposed to always be opposite. So we label it as Q and Q naught. So if we set S as 1 and R as 0, so this is when you're hitting the flight attendant button, you're setting Q to be 1 and Q naught to be 0. And then when you hit the reset button, you're setting Q to be 0 to turn it off, and then Q naught is going to be 1. And then here's our memory. So when S is 0 and R is 0, Q becomes whatever Q was. So it continues to stay as either 0 or 1, whatever it was. So like here, let's say Q previous was 0. We follow it over here. 0 nor 0. This is 1. We follow the 1. 0 nor 1. This is still 0. And then if Q previous was 1, so 1 nor 0 is 0. And 0 nor 0 is 1. So when you keep the buttons both off, it just remembers what it was. Whether it was off or on, it's just going to stay off or on until you interact. Now what happens if you put set and reset? Well, now your input and your two outputs are not opposite of each other, and this is an invalid state. We want to avoid this. So is it clear how this is having a memory? Okay, so what happens if we get that invalid state? What if a child has access to both buttons and decides, I'm just going to press both of these buttons at the same time? What will happen? So here we have our buttons both pressed as 1. So 1 nor this 0 from previously, it's going to make it 0. And then again, 1 nor 0, going to make it 0. And then those zeros are going to propagate back to here. And this is where the child has let go of both buttons. So now 0 nor 0, this is going to become 1. This is going to become 1. And then at the next time step, your 1s are going to propagate back into your NOR gates. 0, 0. So this is going to 1 nor 0, 0, and 1 nor 0. It's going to be 0. And then it's back to this. And then back to this. So it just keeps flipping back and forth if you get in that valid state. It will eventually settle down because of the not perfect delay timings, and it will either converge to 0 or 1 after it's done oscillating. But you're going to have it on and off very frequently if you do get into this state. So we want to avoid it. Well, here's our symbol and just a summary. So SR latch, it's set reset because you have two buttons. One to set the output as 1, and the other to reset your output as 0. And both of those buttons, they just basically control what's being stored with your SR latch. So set is your make output 1, reset, make output 0. And then when you are not pushing either buttons, that's where you're going to remember what Q previous was. And then set and reset, so SR equals 1, 1 is invalid. You're going to get in that oscillating state. So how can we analyze this in a cleaner way? Well, we break up our data path into these two time steps. So here we're calling it the new output. So Q at time plus some delta. And this is my previous output, Q at t. And now when set and reset are 0, and my previous output is 0, that means I'm just going to hold that 0. Same thing for set and reset are 0. My previous output is 1. I'm going to hold that 1. And we can follow this by just doing this. So if you had a 1 here, and your set and reset are 0, so 0 nor 1 is 0. And then 0 nor 0. So Q of t is Q of t plus delta is indeed still 1. and that's going to propagate back to here, and we can get Q of t plus 2 delta in the next time step. So that's how you can kind of be a little easier to follow these by splitting up. It's even though it's the same wire, right? You split it up. This is my new output. This is my previous output. So here we have this different input. So set is 0, reset is 1. I don't care what my previous output was. It's going to become 0. And again, we can follow this. So reset is 1. So Q of t, we don't know what it is. Set, we know is 0. But what do we know if we're NORing with 1 here? I don't care what this is, right? It can be 0 or 1. This is going to become. So that's how you get your reset. And now for our set, I don't care what Q of t currently is. My set is 1. My reset is 0. 1 NOR anything is. And now 0 NOR 0 is. And then we already talked about how this propagates through. It oscillates. Are you guys good with this? Okay, so we want to avoid that oscillating, right? So one thing that we can do is create this extension, a level sensitive SR latch. So this is our SR latch, right? That's what we saw before. But now rather than just connecting S and R directly, we're gonna connect to this thing C. It's usually a clock, and it with S and R. And your clock, it's like, oops, that's a bad one. It's like this square wave function that's periodic. And the idea here is when your clock is 0, your set and reset, they need some time to reach their steady state of either 0 or 1. So while they're reaching either 0 or 1, you can be in the clock of 0, and you're ANDing 0 with S and R. So your actual S and R inputs are going to be 0 while your clock is 0. And then let's say that S and R become stable during this time, right here. And then C becomes 1. And now you have this time period to kind of sample what S and R are actually. Because when C is 1, S is able to pass through, and R is able to pass through. So while they're trying to set up and come to that equilibrium of they're going to be 1 or 0, you can avoid that invalid input of 1 and 1. So here's some more information about clocks. So you pretty much need a clock to synchronize everything. And if you see a clock, it's pretty much guaranteed to be a sequential circuit. And like I mentioned, it's this pulsing signal for not just enabling latches, but it's essentially, yeah, that's the most common use case, enabling latches. Because even the later components I'm going to show you that have memory, they're made up of latches. So your clock period is the time between pulses. So like here, I have the start of a pulse, and this is also the start of the pulse. So this is 20 nanoseconds, right? So that's my clock period. Is that making sense? Okay. And then a clock cycle is one of these periods. So what it's saying by 3.5 is this is 1, this is 2, this is 3. I get 3 point, right? Because this is half period at the end. So that's what it means by the signal above shows 3.5 clock cycles. And your clock duty cycle is the percentage of time that the clock is high. So I have a period of 20 nanoseconds here total, right? And 10 nanoseconds is when it's high. So 10 over 20, 50% duty cycle. So these are just definitions. And then clock frequency is 1 over the period. So we already know the period is 20 nanoseconds. So our frequency is 50 megahertz. And that just means that every second, this clock will flip 50 million times. Any questions about clocks yet? Any of these definitions unclear? Okay. So, I'm going to ask you a question about clocks then. Your poll is open. The code is 089. You answer this on your own first. Monitoring the poll on my phone now, so I don't show you guys the answer. I don't see any new votes coming in, so I'm just gonna ask, does anyone need a little more time individually on this? Or are we all good to go? Okay. So looking at the poll, most people are there. But I think you guys can help each other first. There's enough portion here that you guys should talk to each other first. So discuss and switch your answer if you're convinced. Switch your answer.
You got the same thing? What did you get? Yes, sir. What about B? Well, remember the duty cycle is the percentage of time that it's high. Yeah. Out of all or out of the period, it's the same thing, right?
And it's only,
Just like this period.
Just a single period, you look at like the average overall.
yeah, so it's the ratio
Yeah.
of what, when it's high. And
Yeah.
other periods. Like 60. I didn't think it would be.
Well, remember the period is 4 nanoseconds, so 1, 2, 3, 4. How many nanoseconds is it high?
Six.
Just look at this.
3 out of 4, right?
It's 3 out of 4.
1, 2,
Oh,
3. Okay.
I thought it was like, oh, together.
I think they're all together.
There's a.
Yeah, if you like looked at more cycles.
Also,
So what do you determine the period? Is it based on one cycle or is?
Basically how quick it like gets back to the same point, right? So,
Okay.
yeah, started like, exactly, started like the beginning, and when does it get back to that point? That's a full period.
so it's A,
I think discussion is over. Please change your answer if you were convinced to change your answer. We have moved in the right direction. So I can do this one by one. So A is saying it has a period of 4 nanoseconds. So I'm starting here, right? It's low. And becomes low again here. And indeed here, it just stays low for 1. And it stays high for another 3. So this is one period and this is the second period. So this is 1, 2, 3, 4 nanoseconds. So 4 nanoseconds. And you could confirm that 1/4 times 10 to the 9 is 250 million. So the next thing that we want to look at is what's our duty cycle. So for a duty cycle, we just need to look at one period. So let's just get this first period. So I'm high for 1, 2, 3 nanoseconds out of a total of 4. So that's 3/4.75, which is 75%. So I like B. And we already verified that the period is 4 nanoseconds. So we don't like that. And we verified 2 of these, so we don't like that. So it's D. A and D. Okay. So this is avoiding our oscillating case where S and R are both 1. This is the second addition to that. So we have this clock already to allow the incoming S and R to settle out during the low part of the period before the high part, and it lets it pass through. But that doesn't avoid the problem of having two separate inputs, and a child can hold both of them down, right? So to avoid that, we have one input and we invert it for the R input so that S and R are always opposite of each other. So now we follow these waveforms. So this is our clock. And so D is our input, and it's going to translate directly to S. So this whole part where, oh, I went too far. This part of D is basically ignored because our clock is low at that point. But as soon as our clock becomes high, we can now start propagating to our input S. But that takes some amount of time. And that's why you see this little gap before S is 1. And then once S is 1, it takes, again, some amount of time, like that much, to propagate to our output Q. And then going to our next part, we have D is changing from 1 to 0. So this part is ignored because our clock is still low at that part, right? And then it changes to 1. And once the clock changes to 1, now we can start looking at D propagating through to R to make it 1 because D gets inverted before it goes into R. So it was 0, but it's going to become a 1. And then it does still take some time for R to propagate through this NOR gate to turn Q back to 0.
That propagation time limit how fast your clock can be.
Yes. We'll talk more about that next week. This week, I just want you guys to understand how these lectures work. Next week, you'll understand how timing works for them. And then sequential circuits in general. So now I have this clock with these AND gates to allow that setup time for my inputs. And then I have this inverter to make sure that S and R are always opposites. So this is now a level sensitive D latch. So there's one feature that this level sensitive D latch has lost. You can't have 0, 0 anymore, right? So it's just going to capture D at certain time points when the clock is high. So it's a little different. So here's our D latch truth table. So when clock is 0, basically it's disabled. We don't care what our input D is. Or we're just gonna hold whatever the values previously were. So we still have that memory. It's just only occurring when our clock is low. but we can't directly input 0 and 1 from the outside. Well, I mean 0 and 0 from the outside. It's implicit from this clock and these AND gates. So that's how we get our memory still. And then when clock is 1, we're essentially enabling the reading of D as the input. And when D is 0, reset becomes 1, and S is just connected to D. So that means that Q is going to become 0, and Q naught is going to become 1. That's just from our truth table from before. And then when D is 1, S becomes 1, and R is 0. So when S is 1, we're going to make our output 1, and the inverse of our output 0. So is it clear to you guys what the SR latch does, why we have these AND gates with this clock, and why we have this inverter? Okay. So here's another summary. Basically, the clock controls when you're enabled or disabled. D is the input that you're going to sample from to save as your output. And then when clock is 1, D passes through the Q. So if D is 0, Q will become 0. If D is 1, Q will become 1. And when clock is 0, that's your memory. That's when you're going to remember what Q was before. And this helps us mostly avoid the case where we have that oscillating input. It's still possible. You can have very tight timings on your clock rate and like arrival times, but this makes it a lot harder for, say, a child to make your system oscillate. So we have this one question before we have a break. So level sensitive D latches. So we're assuming all of these latches are holding on to 0 at first. And then we have the input Y D1. And when the clock transitions from 0 to 1, we're going to, like basically one period of clock later, clock is going to be 0 and hold what these things became. What are the stored values in our latches afterwards? I don't see many more votes coming in. Are you guys still thinking about this or no? Maybe one, maybe two, maybe. Okay, let's do one more minute before you guys talk to each other. If you haven't voted yet, get your answer in. And we have quite a nice spread here, which is what I was kind of expecting. So you guys can talk to each other. I don't know if you guys will come to a consensus, but I think having this discussion will be nice. But talk to the people around you, see if you guys all answered the same thing or not.
Yes. What do you think? I thought that at first. I'm not really sure. I think it does depend on like the propagation time. But if the propagation time is fast enough, then I'd say C for both of them.
Yeah.
Well, the output, what do you mean the output? Yeah, so just because it's like a different duty cycle, when the clock is high, I just like was looking at the truth table. Yeah,
So the clock is on and Y on,
the
so
output.
it's gonna be, is it an X
So
or
the output propagates fast enough for all of them. They're all gonna end up
Looking at this thing right here.
propagation time is, I guess you would say,
I like this.
So remember, these are
Yeah, it's
enabled
four
when the clock
times.
is high, right?
as fast
This
as.
clock is high for much
I
longer.
mean,
Does that
obviously,
make sense?
hoping to see that.
So it would have to propagate 4 times,
Yeah.
or at least 3 times
Wait, so
in
what do you get out of that?
So then it
whatever
has
the half of the period. Does that make sense?
It's not like this, right?
I think.
Is it?
So I think
You
you're
get a
probably
key,
right.
right?
It's D, need more information. That makes sense.
One key, two key.
Oh, I see. I see those.
So you like C or B?
But if we need more information. we should
Oh,
know
it's that.
This is.
The propagation time.
Do you know?
Yeah, how do you know what you get here? Is it like based on?
The high duty cycles and part of the duty cycle.
We have to know the propagation time.
Yeah. Oh.
That's just D.
Yeah.
But you actually.
I can't put that answer because it's not on the internet anymore.
Yeah, I mean.
You know where they need more.
There's a one. There's a one. But you have one here. And it's still high. Yeah, I never expect that one.
Oh, they have a-
Yeah.
One is zero right now.
Hey, if your discussion changed your answer, please change your answer.
When it goes to zero here.
Okay. So let's go over this. So first, let's just look at like clock it. 50% duty cycle. And we have, so this is all 0, 0, 0, 0. And our input at our first latch is 1. So while my clock is 0, nothing is going to change, right? But as soon as my clock becomes high, this 1 is going to propagate through and flip this to 1. And then when this is 1, it's going to propagate through and flip this to 1. And when that's 1, it's going to propagate through and flip this to 1 until we get to the end. So the main question that we would have is this clock cycle, its duty cycle, long enough for this input to propagate through all 4 latches or not? So you can see with B, you have a much tighter timing to get this signal through here. So maybe it gets to like the second one, but it doesn't get through here, so it just remembers that I was 0. So you can't really say any of these without knowing the propagation time through these gates and the period and duty cycle of these clocks. But the main thing that I wanted to illustrate here was there's no mechanism to stop it from propagating through all of these. And that may be something that you want. So in the next part, I'm going to show you guys how you can stop it from propagating through. But first, have this 10-minute break. So it's 5:20. Let's come back at 5:30.
Would probably try and.
I don't, you said you were like, right off, right?
Started it.
Inside the seat.
Oh, no, that's the second one.
Yeah, I got, yeah, I do. Gonna make up some red paragraphs. Like, yeah, I could have explained it better.
Yeah, there's a room. I think that's go from there.
It's just, you know, because I'm there, yeah. Please, 1:30. Damn, this room, it's here, oh yeah, it's open the show. That-
Yeah, yeah.
In the rectangular bases and the subtraction, it's kind of key. Dude, he's just like that. Like, fire goes into this. Like, yeah, I hear
I know,
Oh.
all this matrix stuff too.
the shortcut alt equals. So if you do
Practice
it like a
over
quick thing real fast,
Yeah.
and then it's just like almost the same as LaTeX.
Just the,
I don't know if you've ever done,
why is the period
Yeah,
20
for-
nanoseconds?
it's just like a
Because it's also right here.
language. So you just have like
So here it
this,
is.
you can
You're looking
forward
for
slash or
any
backslash
two
P,
spots
and
where
it gives you a P. Forward slash, or you type R and then backslash and
So
back,
this, we can say.
and press your next button and it makes R a factor.
And then there's
This is the first time I tried
10
it
nanoseconds
like this,
of being low
but like lately. it's-
and 10 nanoseconds of being high.
So you're gonna pull some of your low and high from.
It was a caffeinated drink and I brought up.
It's just easy to read.
It just says now dispensing or nothing dispensing. I pressed like the cancel button and it just started showing me like.
And then
the number.
Again, it falls.
So you didn't push like select and cancel at the same time?